Alright, so we are going to move to the next part of this course, the final leg of this course, which is very important part, which is constraint optimization. Okay. So for those of you following the book, this is roughly chapter 12 of Nosable and Right, roughly. Now, in talking about constraint optimization, I'm going to take some extremely simple examples, and they're going to be two-dimensional. And the advantage of doing that is that we can do some geometry. When we can visualize what's going on, then we'll be able to apply it to more difficult problems. Okay, so let's start with something very simple. Let us say my objective function is x1 plus x2. Okay, now you will see that there are some very not so subtle differences between constrained and unconstrained optimization. Problems which make no sense unconstrained suddenly will begin to make sense in a constrained setting. For example, if I give you a cost function like this, f of x is x1 plus x2, and I said minimize this, what would you say? That's crazy, right? Because it makes no sense to optimize something that is going down to minus infinity, right? However, in the constrained world, this may make sense. So let's have a look at that. How? Okay. So let's call this CO. Okay. So in the unconstrained, U is unconstrained optimization, right? So simply the way we wrote it was, this is how the notation for the problem is, right? Unconstrained optimization, I write it like this. In the constraint optimization world, in constraint optimization, right, I have to obviously introduce some constraints for you, right? So let's introduce two constraints. Okay, so I'm going to give you two constraints, and for variety what we'll do is one constraint will be equality, one constraint will be inequality. Let's see what happens. So x1 squared plus x2 squared minus 2 is equal to 0. This is a constraint. Geometrically, what kind of a constraint is this? Circle, right? x1, x2 must live on the circle. Let me, to make matters more interesting, give you one more constraint. x1 plus x2 plus 4. This is what kind of a inequality? I mean, what kind of a constraint? It's an inequality. Right? So very roughly speaking, I have a equality constraint and I have a inequality. Okay. So how do I write this now? So I could write this as one way of writing it is minimize fx. X is the variable of optimization, minimize fx, subject to, right? So many people will write it as s dot t, which simply means subject to. Okay, and your constraints come in basically two flavors. Those two flavors, unlike Baskin Robbins, there are only two flavors here: equality, inequality. There's nothing else that you can really think of. So Cix is equal to 0. I belongs to E is just set of equalities, and Cix is greater than equal to 0. I belongs to the inequality set. So this is how your unconstrained optimization was a simple problem statement like this. Constraint optimization, now I have to write this whole thing. This is my problem statement over here. Okay, is the notation clear to everyone? Cix is equal to 0 for I belonging to the set of equalities. So your set of equalities E, for example, could be 1, 2, 3. That means C1, C2, C3 are equalities, and Cix greater than equal to 0, I belonging to capital I could be 4, 5, 6. So C4, C5, C6, these are inequalities. Simple way of just defining the problem. Okay. Now one thing I want to caution you against, which is a cause of a lot of confusion, when you go from book A to book B to paper C. Every author seems to have a different convention of what an inequality is. So, half the literature will have CIX greater than equal to 0, the other half has CIX is less than equal to 0. So, everything will be off by a minus sign when you are trying to make sense of it. So, for the book that we are following and the notes that we are going to do, we are going to assume this form, CIX greater than equal to 0. Okay. So, keep this in mind when you are reading the literature. If you should go back to the very beginning of the problem definition, make sure which way their inequalities are going, because otherwise you will be off by minus sign everywhere. Okay. So, let us just make one note over here, convention. So, having written this, this looks like a very like a clunky big way of writing a problem statement. We want to have a little bit more compact way of writing it. So, the equalities and inequalities together, they define a very common sense word, they define a feasible set. Means those, it defines those set of x which are legal, right? Therefore, it is also called feasible. So, the feasible set, the usual notation is capital omega, right, will simply be like this: x CIX is equal to 0, I belonging to equality, and CIX is greater than equal to 0, I belonging to inequality. So, this is your feasible set. Is it clear what I mean by feasible set? All those sets of x which satisfy the equalities and inequalities. Okay. Having done this, the optimization problem simply becomes, so constraint optimization simply becomes minimum x belongs to the feasible set f of x, right. So, it is a compact way of just defining the problem. Earlier I just wrote x under min, now I am saying x belongs to a feasible set. Okay. This is the more common notation that you will find in research papers. Okay. Everyone with me so far? So far we have just defined equalities, inequalities. Okay. So, let us just, now that we have done this, let us look at this constraint a little bit. These couple of constraints that we have got, let's sketch them. Okay. The first constraint is an equality constraint, C1x is equal to 0, which we said is the locus of a circle centered at the origin, radius is root 2, right. So, I have, this is my circle. Okay. So, what is this point, for example? Root 2 minus root 2 comma 0, right, minus root 2 comma 0, this is 0 comma minus root 2. Alright, so this is my C1x. Where is my C2x? What is the slope of this line C2x? Minus 45. What is the intercept? Minus 4, right. So, it is in the bottom left, it's like this, right. So, this is my 0 comma minus 4, and this point over here is my minus 4 comma 0. Okay. Very good. Now, what is this feasible set now? Is the entire circle. The entire circle is legal because it's to, it's in this region. So, it's quite obvious that this full region is the dashed green region is satisfies C2x, and the circle itself satisfies C2x and C1x. So, if someone says what is the feasible region of, rather feasible set for this problem, it is the circle, not the green region. The circle is the feasible set. Now, on this feasible set, does it make sense for me to ask this question? Optimize f of x equal to x1 plus x2. It makes sense because the answer need not be minus infinity, right. So, even such a simple problem like this, the moment I start adding constraints into it, they will begin to have some solutions, which in the unconstrained world, this simply did not make sense. Okay. Alright, so that is just a little bit of intuition over here. In terms of notation, I have told you what a equality and inequality constraint is. There is one more definition that gets used a lot in describing constraint optimization. It is called the active set. So the way we define the active set is very simple. It is those equalities are automatic, all equalities are included in the active set. Those inequalities which are, what when I say what, we can arrive at this just by common sense. If I say a inequality is active, what is the first thing that comes to your mind? We are talking plain English here. An inequality is active. So let's go back to our example over here. So in this one, which is the inequality? C1 or C2? C2 is the inequality. Okay. Supposing I am standing at this point, will you say the inequality is active? If I was standing at this point over here, would you say the inequality is active? Okay, so maybe it is not that intuitive. The meaning of active is that the inequality becomes a equality. Remember, there is a greater than equal to. So those points where it becomes equal to 0 is the inequality said to be active. So this point over here is where the inequality is active. That's all. Okay, so this is the definition of the active set. Could have used some other words also. So inequalities are always active because they are always enforced. It's an equality, so you have to satisfy it. Okay. Union with those inequalities which are quote unquote active. So I belongs to the inequality set, which means Cix greater than equal to 0. But for those points, so remember that this over here active set definition, does it depend on x? It depends very much on x. It's a question being asked at a particular point x. At this point, which is the set of inequalities which are active? Active in some sense, in just plain English, means it's making a difference, right? If you look at, okay, let's just quickly draw this once more. This was my C1, okay, and this is my C2. And another case is this is my C1, this is my C3. Okay, let's call this point P, this point Q. Okay, so what are my C1 x is equal to 0, this is my equality constraint. C2 x is greater than equal to 0, this is my second inequality. Over here once again I have C1 x equal to 0 and I have C3 x is greater than equal to 0. Okay. So if I were standing at a point R over here, R is R even a point in the feasible set? It's not a point in the feasible set. So I shouldn't even be asking a question. Supposing I were standing over here, at this point over here, all I can say is that the inequality is active. The inequality is active because C2x equal to 0 holds true at this point. So the inequality is active over here. If I were standing at this point on the circle, am I in the feasible set? I am in the feasible set. What is the active set at this point over here, R dash? Only C1x, because only the equality always has to be there, right? So C1x is there, so the active set has the digit 1 inside it. Okay. C2x is strictly greater than 0 at this point. At this point, C2x is greater than 0. It's not equal to 0. So therefore, the inequality is not active. That is the meaning of active set. Now on the other hand, let's look at the right hand side example. My constraint is C3x greater than equal to 0 along with the previous one C1x equal to 0. So what is the feasible set now? The arc of the larger arc of the circle, right? So this is the feasible set. Now if I ask, supposing I was, let's call this point Q over here. At the point Q, what is the active set? 1, C1 or 1, we'll just say C1. Okay, why? Because the equality is all, you can see the equality is always there by definition. Inequality is not included in this, because why? At the point Q, what is the value of C3? 0 or greater than 0? It's greater than 0. Therefore, it is not included in the active set. On the other hand, if I was standing at P or Q, C3x takes on the value of 0, right? So, if I ask you what is the active set at P or Q, you would say 1, 3. 1 for C1, 3 for C3, shorthand. Okay. So, there are a lot of algorithms that make this distinction between active and inactive inequalities. The rough intuition is this: supposing I am standing at point Q. Now remember, the whole game in optimization, in continuous valued optimization, if someone who has not taken any optimization were to ask you, what is the essential tool that you use in optimization, what would you say? Someone who has not taken optimization asks you, what is the fundamental tool that you use in optimization, whether constrained or unconstrained, what would you say? Something very simple. Anyone should be able to understand. I don't want such a technical answer. Is it not saying simply calculus? Calculus is your tool. Why? Because you work with a gradient, you work with a Hessian, and you move according to that. That's the fundamental tool, right? If someone was doing SVD, what the fundamental tool is linear algebra, SVD. Here, calculus is what allows us to move from a good point to a better point, right? The train that takes us from a good to a better point is calculus. So, I am taking first order Taylor's theorem, second order Taylor theorem, mean value theorem, all of this is built on calculus, right? So, at point Q, I am sitting at point Q. Do I have to worry about C3x greater than equal to 0? Remember, in calculus, what is it? I use first order theorem, Taylor's theorem, I use second order Taylor theorem. What is the real distinction? I mean, when can I use one and not the other? These are all theorems built for a small deviation about a point, right? They are not applicable globally. If I want to write it globally, I have to take many terms of the Taylor's theorem. But if I am taking only first order Taylor's theorem, it's valid in a small neighborhood around the point. If I take second order Taylor's theorem, it's valid in a little bit bigger area, right? That's the intuition behind first order, second order. Now, if I'm standing at point Q and I'm going to do first order, for example, gradient descent, second order, for example, Newton method. Those are the two things that I've used. If I'm in a small neighborhood like this about Q, do I care about C3? Right? So, in a small neighborhood about C3, I'm never going to care about Q. I'm never going to get into trouble with C3. That is the motivation behind saying C3 is inactive. I need not worry about it. On the other hand, if I'm sitting at P or Q, I don't have that luxury. I have to make sure that C3x greater than equal to 0 is satisfied no matter what infinitesimal delta x I move. So, that is why I say C3x is active. So, that is why in an algorithm, when I am deciding how to move from a good point to a better point, I need to do some, keep check of what is good, what is bad, and that checking is happening by defining this active set. So, while it looks like just some definition, it's actually very useful when it comes down to the level of algorithm. Okay. So, this was about, so far we have spoken about definitions, feasible set, active set. These are the two new things that are sort of entered into the picture, right. So, now let us try to solve our first constraint optimization problem. To make matters simple, we will start with one constraint, and even simpler, which is the simplest kind of constraint, an equality constraint. Okay. So, what if C3x is an yeah, then in that case that inequality would never be active by definition, because it's greater than equal to, I mean it's strictly greater than 0, so it would never be active. However, it is unusual to find such a specification. because it's not very well defined, right? If it's C3 is greater than 0, supposing that's my constraint. Now, how close I get to C3 without actually hitting C3 is undefined. I can get 10 to the minus 10 away from it, right? So, it causes a kind of a not a very well specified problem. So, what you will find in the literature is always greater than equal to kind of a notation. Okay, so let's take our previous cost function, simple x1 plus x2, two-dimensional. Okay, c1x is equal to x1 squared plus x2 squared minus 2 equal to 0. So, I have an objective function and I have a equality constraint. Okay. Here is my C1. Okay. So, I mean, this is one of those problems that you can solve graphically. It's very simple to solve. What are the contours of constant cost function value? What would they look like? Remember, okay, let's do a quick revision. For a quadratic form with a positive definite matrix A, what were the contours of constant cost function? Ellipses. For this function, what are the contours of constant cost function? Parallel lines. What is the slope of those parallel lines? Minus 45, right? So, if I draw lines like this, is that correct? Right? Which way is the cost function increasing? To the bottom left or top right? Right? So, f is increasing this way, right? If I go like this, that's actually enough for us to solve the problem. What is the solution? Is there a solution to this problem? Yes. What is that point? The tangent to the circle at the in the third quadrant. That is going to be the solution. So, I already know the solution to this problem. Without the constraint, as I said earlier, this problem makes no sense, but now it makes sense, right? Okay, so that's the reason behind choosing a simple problem like this, that we know graphically what the solution is. Okay, so let's still let us do some calculus over here to get intuition. Okay, now let's try to write down a few things that we will use throughout. Right, calculus is what is the tool that we are using. What is grad f? Scalar vector matrix. Vector size 2 cross 1y, because df by dx1, df by dx2, right? So, df by dx1, df by dx2, what is its value? 1, 1, right? F of x is x1 plus x2, derivative is, what is grad c1? 2x1, 2x2. Okay. So, let's save this first of all. Let's identify a few typical points on this graph that are interesting. Okay, so I've taken a few points over here, A, B, C, D. Okay, I've taken these points over here. Let us denote grad by this color and grad C1 by this color. Okay, so at all of these points, so grad f is a constant, it's a constant vector. So no matter which point I take on the feasible set, grad f is always pointing in the same direction. So let's just draw that over here. Okay. Which way is grad C1 pointing? Inward, outward, any relation to the circle? It's always radially outwards, you can check it, right? At any point if I take, it's always pointing radially outwards. So at this point, it is pointing out radially outwards. At point A, which way is it pointing? Radially outwards, backwards, right? It's pointing over here. Similarly, over here it is pointing here, and over here it is pointing over here. Okay. So at the solution, we know that the solution is out of A, B, C, D, which is the solution point? A. right, at the solution which is point A, is there any relation between grad f and grad C1? They are opposite to each other. In general, what can you say? They are parallel to each other, right? Whether it's pointing in the same way or with a minus sign, they are parallel to each other, right? So, grad f and grad C1 are parallel, okay. So, I could also write grad f of x star, which is the solution, is lambda times grad C1x star. So, we have not derived this. This is just based on observation. You will agree with me, okay. What is the trouble with this way of identifying the solution x star? Is there any other point also where this holds true? It also holds true at C. Also holds true at point C. Okay, so that's a bit of a bummer because we didn't get it directly. Okay. So let's say that we are at a feasible point. Let's make one very simple assumption that no matter what algorithm I use, I always stay in the feasible set. Okay. Let's assume that it's not allowed for you to jump out into, the no man's land. You are always on the feasible set. So let us say that we are at a feasible point and I want to go to a better point. That's the game that we are trying to play, right? That's how it would begin. Pick a random point, get better. Okay. So we are here, we want to go to a better point. Okay. So I am at, let's say, x. I want to go to x plus s, which is better. Now better would mean what? Value of f of x plus s is less than f of x. That's what is meant by better. Okay. Since I said that the rules of the game are that you have to stay on the feasible set, right? What does that mean for C1x? What does that mean for C1x plus s? What are their values? They have to be 0 because I'm only operating on feasible points. This much is true. Okay. Now comes our favorite Taylor's theorem, right? Taylor's theorem, if I apply it to the function C1x, can I do it? C1x is some function, right? x1 square plus x2 square minus 2, it's a function. I can apply Taylor's theorem to it. So, C1x plus s, can you tell me what will it be if I apply Taylor's theorem? Remember, the rules of calculus which I just told you, I want to make a small shift. So, s is a small number comparatively. So, what would I write? Open C1x plus s as? First term, C1x. Second term, grad C1x transpose s. This is my first order Taylor's theorem. Given the rules of the game that I am always going to a feasible point, what does this first order Taylor's theorem imply? It's giving me some constraint on s. It's saying that grad C1 transpose s is equal to 0.